Alright guys, Professor Floyd here. This is Hw3 homework 3, and we are doing problem P. I know I said that wrong in one of my previous ones, and I'll try to put an annotation in or something that pops up on that other one. But this one I said it correctly. So this problem, we are trying to calculate the molecular diffusion coefficient in square centimeters per second or square meters per second of the following particles. And I've got them written up here that they are 0.1 microns, 1 micron, and 10 microns. So we'll start off with the 0.1, and then I think you guys can figure it out for the 1 and 10 because it's just repetition. So we need to remember that our diffusion coefficient is going to be calculated based off of our gas law, our temperature in Kelvin, our Cunningham correction, your friend and mine, the number of gas molecules that we're talking about, which is Avogadro's number, 3 pi, viscosity, and the diameter of the object. So in this case, the particle, 0.001 microns is what we'll be calculating. So one note that your gas constant, you need to choose a gas constant that's going to be in the SI system so that it will cancel everything. You don't want to use the 0.08206 because that's in liters, moles, Kelvin, and we don't need moles in this. Well, we do because we have Avogadro's, which is numbers per mole, but we don't need, it has to be moles because it's the gas constant. We don't need it in liters and atmospheres is what I meant to say. So we've got joules, and remember joules is energy, right? And so that's going to come from pascals and gravity, and so we need to find out what is the alternate unit for joules. How can we express this in units that we're going to be dealing with kilograms or with with kilograms. And so I look it up, and a joule is a kilogram meter squared per second squared. So it's a kilograms meter squared per second squared. So if we incorporate that in, what does that make our R? Our final R and we really don't need that 5, but we'll keep it 8.3145. It's not joules, it's going to be kilograms meters squared divided by moles, Kelvin, and square centimeters. Moles, Kelvin, and I said square centimeters, but I should have said seconds. Seconds squared. Moles, Kelvin, seconds squared. Alright, so that seems like it's a lot of stuff, but when we look up here, we can see that our temperature is going to cancel, our Cunningham has no units, our Avogadro is numbers per mole, and so that's going to cancel. Our units on our viscosity will end up canceling the rest of them, and then our diameter, and so we'll be left with, we should have square surface units per time. So square meters per time is what this should leave us with. And we'll try to work those units out and see if we get it to work out. Alright, so let's start plugging in. And let's just plug in our units first to make sure that this is going to work out. And this is what I did in class. And this is maybe not a bad exercise for us to do just to start off with. So R, the units on R are kilograms meters squared per mole, Kelvin, second squared. Temperature, of course, is going to be Kelvin. I don't need to do that. I can just make my line longer. Kelvin. Cunningham has no units. Number of moles. So in our, we're going to have just some number, but it's implied a per mole. So numbers per mole, which basically means we have moles up here and a number, Avogadro's number. And then our viscosity units, 1.81 times 10 to the minus 5 kilograms per meter second. Is that right? Kilograms per meter second. I'm just going to verify those units on Google here. Ooh, don't want that. And I guess I could have confirmed these on my slides, right? And that is, yes, kilograms per meter per second. Okay. Sorry for the time that used up, but it's important to make sure that it's right. I'm tired of filming these things, so I don't want to film them twice. So kilograms per meter second is in our denominator. So we have kilograms, and then we have per meter second, which is the same thing as having them up here. All right. And what do we have left? We have diameter left, right? So our diameter is going to be expressed in meters. Right now we've got it written as microns, but of course this is 0.01 times 10 to the 6 minus 6 meters. And that's how we're going to actually plug it in for the calculation. So we have meters, and we have meters. So these cancel. We don't have any more meters on here, so these are going to prevail. We have Kelvin and Kelvin. We have seconds squared and seconds. Anyways, we have moles canceling, and then we have kilograms canceling. And what do you know? We have meters squared per second. Yes, we did it. We did it. All right, so now we can plug in our numbers and know that they're going to work out correctly. So our numbers are 8.3145, and those were the units. Our temperature needs to be expressed in Kelvin, and so what did we say? We said assume this is 20C. So 20C is 293.15 Kelvin. We're going to leave that off, and I'm leaving off my units for this. Kelvin. Our Cunningham correction factor. Oh, nuts. That old Cunningham correction factor. We've got to calculate that. So if we remember, Cunningham correction factor, I'm sure you guys do remember, is 1 plus 2.52 lambda divided by the diameter. Okay, so I just erased that our diameter that we're calculating for is 0.001. So I'll go ahead and, so we're going to have to put our Cunningham correction in. Our Avogadro's number is 6.022 times 10 to the 23rd. 3 pi, I'm not going to write that one in, pi, 1.81 times 10 to the minus 5, and our diameter is 0.01 times 10 to the minus 6 meters. Okay, so now that I've got that stored, I can focus back on Cunningham. So the Cunningham, if we calculate this using this crude way, so some of you guys have been busting my chops over Cunningham correction factor not matching up when we use this rudimentary way. I showed you in the last post that it's equation 320 out of the Heinz book, Aerosol Technology. Knock yourself out with that. I went ahead and modified what we find. I modified the file that I posted online that you can find on D2L for Cunningham correction factors. And I put in that nice long equation, equation 320, and then drug it down so that you get the actual Cunningham correction factor if you want to look it up in that table. So in the future, if you really want to be precise with your aerosol calculations, you now have that. And I checked it out with the book, and it works out c'est magnifique. So for right now, we're just going to do this ballpark estimation of Cunningham correction. So 2.52 times 0.066, which, I'm sorry, our lambda is the mean free path, 0.066. 1 plus 2.52 times 0.066 micrometers, and then that divided by the diameter, 0.01 micrometers. Again, Cunningham correction is unitless, divided by 0.01 plus 1. Alright, so we should get a Cunningham correction factor that's pretty large, and it should be in charge at 17.63. So in we go with Cunningham correction, 17.63. And now it's time that we can just calculate these things out. Alright. So I have not worked this one previously, so we'll have to see if we do it correct together. 8.3145 times 293 times 17.63 divided by Avogadro's number, 6.022 e to the 23rd, divided by 3, divided by pi, divided by 1.81 e to the 5 minus, whoa, e to the 5 minus, divided by 0.01 e to the 6 minus. Alright, so when I punch that in, I'll put it back in scientific, I get 4.18 times 10 to the minus 8 meters squared per second. Since we've already worked out our units, we know that that's going to be correct. Alright, and now I can also look that up in my Heinz book and let you guys know whether we did it correctly or not. So for a 0.01, our diffusion coefficient, 5.45 times 10 to the minus 8. So Heinz gets 5.45 times 10 to the minus 8 meters squared per second. So I wonder if that's because we're using the dumbed down version of the slip correction. So the way we could tell that is we can see the slip correction, the true slip correction is 22.976. And so if we look at the ratio of what we should have had to what we did have, so basically if we look at 22.976 compared to what we used, 17.63, that should be the same ratio as 5.45 to 4.18, and that should equal 5.45 to 4.18. Now let's calculate it and see. Now I'm really going on a limb because I got 13 minutes invested into this. So 22.976 divided by 17.63, that comes out to 1.303, and 5.45 divided by 4.18, 1.303. How about that? So Cunningham correction factor does make a difference, but for the purposes of what we're doing, using the simplified version is fine. On the exam, you will not be able to look it up, and you're not going to have access to outside material, so I want you to be able to calculate it. So knowing how to calculate it using this simplified technique is important. It's close enough, we get in the ballpark, and so if I say the diffusion coefficient is 4.2 instead of 5.5, that's not too bad, but it's not great. Alright, well that's our answer, and that's what you'll be graded on. I expect you to come out with this same answer, or something very similar, unless I've made a typo. Alright guys, over and